Hi, welcome to this lesson on calculus, sketching cubic functions. Let's have a look at question 2. So we're given the cubic function x cubed plus x squared minus 5x plus 3. So it's currently in the general form ax cubed plus bx squared plus cx plus d. So before we do anything, we can notice some properties of this cubic function. Well, first of all, the value in front of x cubed is a equals 1, which is a positive number. So it should have a general shape of an increasing, decreasing, and then increasing function. And because the d value is positive 3, we know that the y-intercept is going to be 0, 3. Okay. The first question asks us to show that x minus 1 is a factor of f of x, and then hence to factorize it. Well, to show that x minus 1 is a factor, by the factor and remainder theorems, we must show that when you plug in x equals 1, okay, positive 1 here, then you must get 0. So f of 1, that's 1 cubed plus 1 squared minus 5 times 1 plus 3. Okay, 1 plus 1 is 2, plus 3 is 5, minus 5 is 0. So therefore, x minus 1 is a factor of f. Okay. And now, to factorize it, all we need to do is show that we can write x cubed plus x squared minus 5x plus 3 as a factor of x minus 1 times some quadratic expression. Okay, well, now we can use a bit of logic. Well, to get a x cubed, I need a x squared here. So when I expand those out, I get x cubed. And to get a constant of positive 3, I'm going to need a negative 3 here. So when the constants multiply out, I get positive 3. So I just need a plus bx term here. And again, I can use logical inspection, or I can do polynomial long division and get the same quadratic expression coming out. So what I'm going to do is I'm just going to analyze the x squared terms. Okay, so on the left-hand side, it's just x squared. And on the right-hand side, it must be, well, x times bx gives you bx squared. And negative 1 times x squared gives you negative x squared. Okay, so I can add x squared to both sides, and I get 2x squared equals bx squared. So therefore, b must equal 2. Okay, so this is equal to then x minus 1 times x squared plus 2x minus 3. Okay, so now look at this inner expression here, and I'll ask myself, can that be factorized? Okay, so first of all, factors of 3, or it's only 2, right? Because 3 is prime, it's 1 and 3. And can I get a difference of positive 2? Well, if I take positive 3 minus 1, that'll give me positive 2. And then 3 times negative 1 will give me negative 3. So I can further factorize this as x minus 1 times x plus 3 times x minus 1. Okay, and if you expand that product out, you'll get this exact quadratic expression. So we have here, there's two factors of x minus 1. So it's x minus 1 all squared, because you're multiplying x minus 1 by itself, times x plus 3. Okay, so that is the fully factorized form of the cubic function given by f. Next, we want to determine the coordinates of the intercepts and the turning points. So for the x-intercepts, the reason why we like to factorize is because, as we saw, that's equal to x minus 1 all squared times x plus 3. Okay, so now the x-intercepts is when this expression is equal to 0. So that's why we need to factorize, because now I can use the zero property of algebra. Each factor must equal 0. Okay, x minus 1 squared equals 0, or x plus 3 equals 0. So for this one here, you just left with x minus 1 equals 0 by square rooting both sides. And then x equals 1 by adding 1. And then here you're going to get x equals negative 3. So the x-intercepts are at positive 1, 0, and at negative 3, 0. So those are your two x-intercepts. For the y-intercept, well, you now substitute x equals 0. So for the y-intercept, you're going to put f at 0. And we saw that when you put 0, you're going to get 0, 0, 0, and just left with 3. So therefore it is 0, 3. Okay, so those are all the intercepts. What about the turning points now? Okay, so for the turning points, so for the x-intercepts, knowing the factorized form is great. For the turning points, it's better to know this form, the ax cubed plus bx squared plus cx plus d, because now we can use the power rule and then sum and difference laws for derivatives. So f prime x, using the power rule, that's going to be 3x squared plus 2x minus 5. Now for your turning points, that is when your first derivative is equal to 0, because these are the stationary points for the cubic. So you're solving 3x squared plus 2x minus 5 equals 0. So I'm going to use the quadratic formula here. Okay, you can try and factorize it if you want to. Most likely could be, but I'll just go with the safe bet. So that's x equals minus b plus or minus square root of the discriminant term, b squared minus 4ac, all over 2a. Right? Okay, so b is positive 2, so it's negative times 2, plus or minus the square root of 2 squared minus a is 3, so 4 times 3, and c is negative 5. All over 2 times a, which is 3. So therefore, I get two values, x equals, so let's bring up our calculator and then work out that value. Okay, so for the first one, I'm going to put negative 2 plus square root. 2 squared is 4 minus 4 times 3 times negative 5. And then all over 2 times 3, which is 6. So I get x equals 1, which is great. Or x equals, so let's go up here and put a minus sign. And we get negative 5 over 3. Okay, but notice that x equals 1, that is also an x-intercept. And that is no coincidence. Whenever you factorize a cubic function and you have a repeated factor here, x minus 1 is repeated, it's repeated 2 times. Then not only will that be an x-intercept, it'll also be a turning point. And that is a general rule for cubic functions, which is really good to know. So if you see a factor that's repeated squared in a cubic factorization, you can already know automatically two things. It's going to be an x-intercept and it's going to turn at that point. Okay, so at 1, that gives you f of 1 is 0. Okay, it's x-intercept. Or at negative 5 over 3, we need the y value. Okay, so I'm going to shift store that value into a, so that when I put it into the original expression here, so alpha a cubed plus alpha a squared minus 5 times alpha a plus 3. Notice if you put it in this one here, x minus 1 all squared times x plus 3, you will get the same answer as well. Both these forms are equivalent. They're just different structures, but they are equivalent. So I get 256 over 27. 256 over 27, and I just want to get a feel for what number that is in decimals. 9.48, so just say approximately 9.48 to 2 decimals. Okay, so that is the intercepts and the turning points. What about intervals of increasing and decreasing? Well, we said for increasing, that is when your first derivative is greater than 0. So again, the first derivative was 3x squared plus 2x minus 5 greater than 0. And we did find the critical values. Those are the stationary points. So there's that x equals 1 or x equals minus 5 over 3. So if I draw my number line, which I need to in an inequality, so negative 5 over 3 is over here, positive 1 is over here, open dots, okay, because you're not including the value of 0. So let's take a value bigger than 1. So remember, you're putting it back into this derivative function now. So what we're testing on the number line is f prime of x, not f of x. Okay, so if I plug in, let's say a number bigger than 1, let's say 2. 2 squared is 4 times 3 is 12. 2 times 2 is 4 minus 5. So it's going to be a positive number. Then let's take 0 in between. That's in between negative 5 over 3 and 1. Then I'm left with a negative value. And then if I take something much less than negative 5 over 3, so negative 6 over 3, that's negative 2. Well, negative 2 squared, positive 4 times 3 is positive 12. Negative 2 times positive 2 is negative 4 minus 5. That's still going to give me a positive output. So increasing is when it's positive on the interval. So therefore, x is increasing on the interval minus infinity to minus 5 over 3. Union, so it starts up again at 1 to infinity. And then where's the function decreasing? Well, we've done all the hard work for the interval. So that's when f prime x is less than 0, so negative. So that implies x must be an element from negative 5/3 to positive 1. Okay, so that's the interval of decreasing. So remember, your graph is going to decrease, so it's going to have that downward trend. Okay, and then your graph will increase, so it'll have these upward trends. Okay, for that interval. Intervals of concavity. So now let's recall, for concavity you need the second derivative. So let's recall the first derivative was given up here as 3x squared plus 2x minus 5. Now the second derivative, we take the derivative again of this expression. That's going to give you 6x plus 2. So let's see, for concave up, the property algebraically is the second derivative must be greater than 0. So that implies that 6x plus 2 is greater than 0. This is a linear inequality, so we can solve it as follows. Bring the 2 across, so greater than negative 2. Divide both sides by positive 6, so x is greater than negative 2 over 6. Negative 2 over 6 simplified as negative 1/3. So on the interval, x is an element from negative 1/3 all the way to infinity. The graph is concave up. What about concave down? Algebraically again, that's when your second derivative is less than 0. So again, we're solving the linear inequality, but less than 0 this time. So let's take 2 across, less than negative 2, divide both sides by 6, and we get x is less than negative 1/3. Okay, negative 2 over 6 simplified. So on the interval, x is an element from negative infinity up to negative 1/3. That is concave down. So it'll have that concave down shape, right? Which just means again that the graph lies below the tangent line. So it's down from the tangent lines. And then let's recall for the concave up one, it's going to have this shape where the graph is above, it lies up from the tangent lines. And then lastly, inflection points, if there's any. Well, I think that's going to be the next one. Let's just check. Yeah, so if any. So we know that the second derivative is what? It was 6x plus 2 that we worked out. So if we set that equals to 0 and solve, we get x equals negative 1/3. But how do we know if it's a point of inflection? Well, we know that x coming from negative infinity to negative 1/3, this was concave down. Then you have x equals negative 1/3. This is where you have a potential inflection point, but that's only true if from negative 1/3 to infinity, did we see a change in concavity? Yes, that's concave up. So it goes from concave down, changes the inflection point and goes to concave up. Okay, so therefore at x equals negative 1/3, so let's find the function value at that point, and then we'll have the coordinate for the inflection point. So again, what I'm going to do is I'm going to say negative 1 divided by 3, and go shift store into b now. Okay, and then I'm going to take into the original function, so it's going to be b cubed plus b squared minus 5 times b plus 3. That gives you 128 over 27. Okay, so we'll find what that is approximately, but coordinate-wise, it's negative 1/3, comma 128 over 27. So that is about 4.74. Okay. And lastly, we need to just sketch the graph of this function. So first of all, let's recall in factorized form, it was x minus 1 all squared times x plus 3. So our x coordinates, the intercepts, was at 1, 0 and negative 3, 0. Then we saw that there was a y-intercept at 0 and 3. Okay, so those are the intercepts out of the way. Then it says turning points. The turning points were at 1, 0, and then negative 5/3 and 9.48. So let's come back here. So negative 5/3 is almost close to 2, so it's about here, close to negative 2 rather. And then the y value was around 9.48 approximately to 2 decimal places. So let's plug that in there and make sure to label your coordinates, very important. What I always do is I like to just put the exact value as a fraction, so 256 over 27. Okay, so that there's no confusion on the exact value. And then the other one was at 1, 0. So that turns at that point there. Then it said the graph was increasing from negative infinity to negative 5 over 3, so the stationary point. And then from the stationary point again, it was increasing. Okay, so we know that it's going to increase. So I'm just going to put it in dotted lines for now. It's going to increase up to that interval. Then we saw that it also actually decreases and it goes through the turning point. So let's just arc that a bit better. So it goes through the turning point, comes down to the other turning point while it decreases, and then begins to increase again. Okay, so I'm putting it in dotted lines because I also want to get the concavity, the bendiness of the shape correct before I put it in solid lines. Okay, then at negative 1/3 and 4.74 approximately, that is the inflection point. Okay, so negative 1/3 is roughly about here. And then it was like 4 point something, right? What is it? 4.74. So it's roughly about here. So negative 1/3, I put the exact fractional value, 128 over 27. And then that's where it changes the concavity. So what I'm going to do for the concave, let's see up here. For concave up, it's from negative 1/3 to infinity. So it's going to have this bendy shape like that. So let's go from negative 1/3, that's over here. It's going to bend downwards, okay? So it bends downwards like that and keeps bending like that. Okay, so it lies above its tangent lines, hence it's concave up, and it goes through the y-intercept. And then it was concave down less than negative 1/3. Let's check that. Yes. So that's going to be this bendy shape like that. Okay, and then it bends down more like that. Okay, so it lies down from its tangent lines. So all the tangent lines are above it essentially. So it lies down from the tangent lines. And then for the other one, concave up, that means it lies up from its tangent lines. So all the tangent lines are below it. Okay, and that is the full accurate sketch of this cubic function, given the turning points, stationary points, the x-intercepts, the y-intercept, a point of inflection if there was, and where it was concave up or concave down. All right, so that's how we would do this type of question. I'll see you in the next one.